Hi, this is János, Real Audio, and I have almost 10 minutes to shoot a video. So here I come, and let's talk about whizzer cones and how they affect the sound of a single driver. So basically, I got a really nice comment that it is his understanding that the big cone itself creates the lower frequencies and the small cone, the whizzer cone, the high frequencies. Is that so? And the answer to that is yes. However, what percentage of the low frequencies the big cone is able to reproduce? What is the dispersion of that? How even the response it is? That's highly dependent on the shape of the cone and the ratio between the size of the big cone and the whizzer cone. So basically small cone and big cone. And there are several considerations about that. One, the bigger the size difference between the two cones, the less coherent that driver will sound. So when you have a driver that has like a really huge, let's say like a 15-inch main cone, and it has a tiny whizzer cone, like this type of situation, then you will have a gorgeous mid bass from the big cone, and you will have like 10 plus kilohertz response from the whizzer cone in the center. But the I would say the 2 kilohertz through 8 kilohertz region will be suffering, that will be lacking, because that region does not have proper coverage. If they would make the whizzer cone much bigger, let's say that big instead of that small thingy, then that region would have nice coverage, but then the price would be that the 10 plus kilohertz region would not have a coverage. So that's why choosing the sizes for the whizzers and the geometry has everything to do with the frequency response, the frequency range that a single driver can reproduce. And also, let's look at how the shape of the whizzer cone is and what is the profile of the two cones. So let me just draw you it from the side, because that was from the front when you look at it from the front. But when you look at it from the profile, let me just draw it fast. So this would be your main cone. It's like a V shape, like a very shallow V shape. And then up to this point, this could be a regular woofer. And you just put a dust cap here, and that's it, you have a woofer. Instead of putting in the dust cap, you put in a whizzer cone that looks like this, right? A whizzer cone. And now you get a single driver. And based on so if the angle of the whizzer cone's cone and the angle of the main cone, the more different they are, the more divergent the dispersion pattern of the two will be. So that's how when you move you around, then you will notice a greater change in the balance of the lower frequencies and the frequencies covered by the whizzer cone. So what you want to look for in a balanced whizzer cone is something like, let's say, let me draw it like this. So instead of the whizzer cone being like really like a narrow cone type, it should be more of a flatter cone. So when the angles are more approximate between big cone and small cone, then you have a more uniform distribution pattern, dispersion pattern coming from the two. And how can you predict and look at what are the frequencies, what's the high frequency limitation reproduced by a single driver, is you have to look at the diameter of the voice coil. What is the throat of the whizzer cone? Because when you look at every single driver, unless it's a flat driver, let's say like Magnapans, all of the cones have a profile, this V-shaped profile, and that means that without exception they are horn loading the band that they reproduce. And what is the band that they horn load? If you look at horn theory, the highest frequency that the horn is amplifying, or we would say where it improves the coupling efficiency between the energy transfer from your membrane to the air, the highest frequency is defined by the wavelength. That should be just one. I cannot draw like this. So just that's like a sine wave. So the length of the sine wave that corresponds to the throat of the whizzer cone, that's the highest frequency where it will have considerable output. That will limit the high frequency strength of the working range of the whizzer cone. And now, let me just draw it this way. The half wave produced that corresponds to the diameter of the whizzer cone, that half wave is the lower limit where the whizzer cone has strong output. And the quarter wave that corresponds to the whizzer cone's diameter is the effective lowest wavelength where the whizzer cone will have a significant output. Same thing is true for the main cone, and not just for single drivers. Every single driver, that where you have the throat, which is defined by your dust cap basically, that's the highest frequency that it amplifies. For example, looking at my Altec woofer, that corresponds to 3.6 kilohertz roughly. And what do you think? Where does the 515C has breakup modes? There, at that frequency, 3.6 kilohertz. Why? Because that's where the dust cap changes the loading. So it's not just a throat there, and not just a flat throat, but it's a dust cap. So it's bulging out, and here by these regions, so the sound here is going forward, and the sound here is going to the side, and going here, and then bouncing off the membrane. So it's not everything just going up and down, but here these frequencies you have a mess, and that's why you have those breakup modes for your driver. And when you look up the diameter of the dust cap, from that you can tell where the breakup modes will happen for the cone at the high frequencies, which are due to the problems with acoustic coupling to the air, which are independent from the cone's main resonant frequency that depends from the instability of the cone. So even if you have a perfectly stable cone, you will still have these breakup modes defined by your dust cap. So what else? I think that was it. My time is up, and I hope now you know a little bit more about whizzer cones. There's so much more I wanted to tell, but it does not fit in the time. So have an awesome day. Please like and subscribe. Bye bye.